Hello and welcome to another Data Scholar Code Along. And in this project, we are going to classify SETI signals to aid with the discovery of extraterrestrial life. Now, a bit of context about this particular project. The data that we're using today comes from a SETI Institute hackathon, which was hosted in 2017. And basically what they wanted to do was, improve their radio telescope signal classification tools using the latest developments available in machine learning and deep learning at the time. So the data that they were able to provide are radio signal data, and it's in a spectrogram format, which is basically a 2D visual representation. And what we can do is the pixels are stored in an array at the moment. So that's why we have images as a CSV. And what we do is convert them and plot them back into pretty much an image, and we use a convolutional neural network to classify them images. Okay, so let's jump straight into it. These are the imports that we need. I'm not going to type them out just to save time, but if you pause the video and take a look, copy all them into your workspace and you should be good. We've got the pandas, numpy, and the matplotlib. We use TensorFlow. This one here, live loss plot, the plot losses keras. I'll go into what that does a little bit later on, but you may have to, if you're using Google Colab, you may have to install that. Oh yeah, so pip install live loss plot, you should be good. We use some scikit-learn metrics like a confusion matrix, and we also import the general matrix package. We set the random seed to 42 because that is the number with all the answers in the universe. Thought it would be quite apt to use. And we use the warnings. We get rid of them to ignore them. So anything that's due to be depreciating stuff won't pop up and annoy us. We use the magic function to keep our graphs nice and tight within our workspace. And then just to make sure we're all on the same page, let's run that and make sure that we all have the same TensorFlow version installed. Google Colab is 2.11.0. I would upgrade or downgrade depending on what your version is. I believe at this time of recording, 2.11 is the most recent version. So just double check that so we're on the same page, just so you don't run into any difficulties if you were trying to code along today. Okay, so let's import the data here. As you can see, we've got the data and it's separated into the train and validation sets with both the images and the labels there. So let's get them over into our workspace. So train images, we need to use pd read CSV, and it's data train, and then the images, that's CSV. And now the data is available on SETI, and I believe it's on Kaggle as well. I have to double check that, but you can pull that in and follow along or use any other. I mean, if you use any other sort of radio signal data, hopefully it's in the same format, and you probably get different results. But let's just crack on with this particular data set. As I say, if you need it, it's available on the SETI website and Kaggle. Okay, so because I already know this data frame doesn't have a header, we need to set that as none. And why have I put a comma there? Nobody knows. Let's copy and paste that, and we'll call that labels, and we'll change that to labels as well. And then we'll copy both of them, and we'll do the same for our val as well. So our validation data, we just have to change a couple of bits and bobs there. It's actually called validation, isn't it? Not just val. That. There we go. And if we set that to run, it'll take a couple of seconds just because the data is quite a large data set. So once that's run, we will have a look at the train images head. There we go. And as you can see, there's our observations. Each line's an observation. And these are our radio signals basically put into individual pixels. Okay, so let's look at the labels that we are using. And these are used what we need to classify. So we've got 4 labels. 0 is a squiggly band. 1 is a narrow band signal. 2 is noise, and 3 is narrow band DRD. These definitions are available on the SETI Institute website and also on Kaggle. I haven't got time to go into it in too much detail there, but basically we've got them 4 classes. Negative, all them are negative, and that one's a positive. So we're pretty much looking for squiggles really, to separate what could be an extraterrestrial signal, as far as if that my interpretation of that is correct. Okay, so what we're going to do now, let's take a look at the shape of our train images and our train labels. We print them. There we go. We've got 3,200 observations. And this number here, 8192, 8,192, they are our pixels. And originally they were distributed by a 64 by 128 matrix. And that resultant number, 8,192, is the product of that particular matrix. Okay, let's do the same with our validation, and we'll take a look at that. So again, we've got 800 observations, the same amount of pixels, and we've got 4 classes in for each of them 800 observations. Cool. So now what we need to do is create our X train, X val, Y train, and Y val, and we need to reshape the NumPy array. So we basically rebuild the images that it originated from. So let's just do our X train first, and they will be train images. We'll take the values of what's in there, reshape, and we need to reshape them to the number of observations we've got, the 64 width and the 128 height. And because we don't have any color information, we set the last argument as 1, which is grayscale. Okay, let's do the same for our xval, and that will be val images values dot reshape, and we'll do the same, but we need 864, 128, and our grayscale. And we need to do the same for our y, so we might as well just copy and paste that. Set them to y. We need to change them to labels and labels, and we only want the values, so we can get rid of the reshape part as well, and we should be good to go on that. So let's run that, and there we go. So let's visualize what we've just done. So we'll plot the spectrograms. So we need the figure, and we'll set the fig size to something. Let's just set it to 15. It should be big enough to see what we're playing with. And so we need to write a for loop now. In range 1 to 4. Create a subplot. So subplot, and we want 1 row with 3 columns and I. Okay. And then what we need to do is create now the image from the NumPy arrays. And what we need to do is set that to squeeze, as we need to drop a dimension. And if we input train, and we want to randomly select them as well. So let's do random.randint. Just randomly select them from the train. And that's easy to do. And we'll just set the, X from 0 to X train shape. And we should be good. That'll select 3 random images every time we refresh. X ticks, we will set that to an empty list. PLT, do the same with the Y ticks as well. Okay, and then we need to actually show the image. So IM show, and it'll be our image. And we need, because it's grayscale, we need to set the color map to gray in the American spelling. So if we run that now, oops, what have I done there? A value error. Where have we got that? MP squeeze or something. What have I done there? MP squeeze image. What have I done? I forgot to put shape. That's what it is. There we go, and that should work fine now. Okay, so there we go. And if we keep running that, that'll just like shoot us through randomly selected images. And as you can see, I imagine that one's our squiggly one. But there we go. And I imagine that one's a noise one. And then narrow band and narrow DRD, you probably need some specialist sort of analysis after we classify it. But there we go. Okay, now the next stage, we need to create our training and validation data generators where we will also add some data augmentations to our images. So we'll take the images we've already got, make new samples with various different sort of augmentations, so like horizontal flip, rotation range, and things like that. And this is really the part where you can experiment. Experiment with different kinds of augmentations set at different values and whatnot, and see if you can squeeze performance from your model. So we need to import from Keras pre-processing, and then images, or is it image? Yeah, it's image. Import image data generator. So we'll make the first one data gen train, and we'll set the image data generator, and I'll do a few here. So from memory, horizontal flip, set that to true. Rotation range, set that to 0.2. Width shift range, we'll set that to 0.2 as well. And height shift range, we'll set that to 0.2. Now, if you use exactly the same as me, I would, basically recommend to check and check them. Do the for the first run, maybe do exactly what I do, but then to experiment more and try and push more performance from your model, tweak the numbers, add more augmentations, take some away, replace them and whatnot. Just experiment, and you'll understand how different augmentations on images affect the performance of your model. So now we need to get this data gen for the train and fit it to our X train. Okay. So the next thing we want to do, we can just basically copy this, and we'll do the same for our val. So just call that val, and we need to have that as well. Keep and do exactly the same augmentations just to make it fair on your training and validation as well. So then we need to change that to val as well. Okay, so I can run that cell, and that'll build the image data generators. And just a little tip: if you are not really familiar with the image data generator and its arguments, if you're working in Google Colab or Jupyter, it works in Jupyter Notebook as well, I believe. Image data generator with a question mark. If you run that cell, it'll give you the doc strings of it, and it'll give you some various different arguments and what your values you can set and things like that. So it's a good way to take a look and experiment yourself. Okay. So what I'll do, I'll just delete that cell because we don't need it. Now we're going to create our convolutional model. I've got the imports here. So again, if you want to pause this video and copy these into your workspace, we are importing, our layers, models, optimizers, and callbacks. And I'll explain what these do when I've coded our model. I'll go back through it and explain what each sort of attribute of the layer does and how it affects our model and whatnot. So let's just stick to having stick to time and get coding. Okay, so let's initialize the CNN, and we want model. I will tell you what I need to do first. I need to run that cell. There we go. Model sequential. Okay, and we will write our first convolution. That's not how you spell it. convolution. Okay, so model.add, very easy with the Keras API. So we want to set 32 filters. We want a kernel of 5 by 5. Padding, we want the same. And then we need to enter the input shape of the data that our first layer is going to receive. So if you remember, it's 64, 128, and 1 color, which is grayscale. Next, we're going to add a batch normalization. Will it finish it for me? Yes, it will. Layer, well, part of the layer. And we need to add our activation. Will it finish it for me? Yes, it will. And we want to put a relu activation function on that. And then we need to add our max pooling 2D and set the pool size to 2. And then we'll add dropout, and we'll set the dropout, quite conservative, 0.2. Again, these sort of things are places where you can experiment and see how it changes the model in terms of like how many filters you have, and your padding as well. That may affect your model for the positive or negative. But data science, machine learning, it's an iterative process. Try 10 things, only one works, but it's a good learning experience anyway. So we'll do our second convolution. My spelling gets worse as time goes on, I swear. Okay, and we'll add conv2d, and this time we'll add 64 filters. We'll keep the kernel the same size. Padding equals same. We don't have to put the input shape here and the second one. Yeah, I'll tell you what we'll do. We can just copy that, can't we? We can copy that. You don't have to type all that out again. There we go. Cool. Okay, and then we'll only do 2 layers, and then we'll do a flatten. Why can't I spell? Model.add flatten. And then we will do our fully connected layer. So let's do model.add dense. And we'll have 1024 nodes or neurons, or however you want to call it. And then we can take these as well. We'll take them and we'll do the same. But this time we will force a bit of performance out, and we'll make our neural network work for it. So we'll increase the dropout to 0.5. And then finally, we need to create an output layer, model.add, and it'll be dense. And because we've got 4 classes, we will have 4 nodes. And then the activation, not activations, it's activation. And we will use a softmax to bring back a probability scoring for each prediction. Okay, so what have we done here? We've implemented a model, a sequential model, and what our first layer does, the first point is a convolution. So what a convolution does is basically look at the relationship between pixels by learning image features using a small square, which is our kernel. So it's a 5 by 5 square. And so so these are how many filters the convolutional neural layer has, and then we've got the square filter, the kernel. Okay. What we have to do then is put the padding the same, so it doesn't padding. Padding is basically it refers to the amount of pixels added to an image when it's being processed by the kernel, so our 5.5 kernel. So that's what the padding does. And then we've got the input shape, as I mentioned earlier, is we have to define the shape. We have to let the model know what to expect, basically, from our data. And then we have our batch normalization. This layer it makes the training of a neural network a lot more stable and quicker as well. And what it does is it normalizes the layers inputs by recentering them and rescaling them. It was, I believe, if memory serves, it was first sort of introduced around 2015. So it's one of the reasons why neural networks have come a long way, especially when they've become more stable and faster to train. And then we have the activation layer, and that is basically ReLU is a non-linearity. So it'll, in simple words, it basically lets the model learn complex functions. And then we have the max pooling layer. So what the max pooling layer is, it reduces the dimensionality of the convolution. So it reduces the dimensionality while sort of preserving the important features of our image that are being extracted by the convolutional layer. And the dropout is being set to 0.2, and that will basically kill 20% of the neurons, and it helps the neural network generalize better, and it avoids overfitting the data. So that's what happens on each of these. Okay, and then what we have is the flatten. So what that does is basically it takes our output of these two layers and flattens it into a um, a single dimension. A single dimensional vector, and that then feeds into our dense layer, our fully connected layer. Then we've got the amount of nodes we've got there. We've got the activation, as same as above, same max pooling, and then it finally enters the output layer, and the output layer is the one responsible for giving the actual prediction. And because we've used a softmax activation, it will give us a probability of what particular class a particular image falls under. So that's what we've built there. Feel free to experiment, change a couple of the figures, change the hyperparameters, and just see what happens. And it'll be very interesting if you post in the comments what sort of accuracy you've got, and what sort of F1 score and precision and all that kind of thing you've got by amending these different values. Be very interesting. Okay, so what we're going to do now is build a learning rate scheduler, and we're going to compile the model as well. So let's set an initial learning rate, and we will set that to 0.005. Okay, so let's create a scheduler. So we need tf.keras optimizers exponential. Okay, and then we'll set the initial is it the initial learning rate, and we set it to initial learning rate, which we defined as 0.005. We set the decay steps, and we'll set that to 5. And then the decay rate we'll set to 0.96, and then staircase equals true. So what it'll basically do is adjust. It'll basically decay the learning rate as the epochs go, and hopefully it'll help us, get to the local minimum a lot quicker and have a really strong model that is able to generalize really well. And we will do that using the mod optimizer Adam, which is a form of stochastic gradient descent. So learning rate, we'll set that to our LR schedule, if I can spell it. There we go. Okay, so we can run that. Invalid syntax, what have I done there? Oh, that's because there's a full stop and not a comma. Bingo. No. Exponential decay. Have I spelled that wrong? I have, haven't I? That's why. I am terrible at spelling. Exponential decay. That's how you spell it. There we go. Get there in the end, don't I? Get there in the end. Okay. So now we're going to compile it. So model compile. Optimizer equals optimizer. We need to set the loss, and as it's a multi-class classification, categorical, my spelling again, categorical cross entropy. And then our metrics, we need accuracy. Okay. So let's compile the model. The model is not defined. Why not? That's because I haven't run this layer. There we go. I'm too busy talking. Input layer is incompatible with the layer expected for them found too. So what have I done there? Pool size, input shape, max pool size 2. And that's because we don't need a max pooling size. I am victim of my own copy and paste. I should have copy and pasted the batch normalization, but I've done it wrong. So there we go. Let's run that again. That should be fine. Happy days. Here we go. So run that schedule again just in case, and let's compile the model. There we go. Compiled. Now let's check out the model summary. Model.summary. And it's got, there we go. So there's all our layers. And we're getting total params as 33 million, well, yeah, just over 33 million and a half. And non-trainable params are 2,240. And what these indicate is, the non-trainable ones, is it's just the number of weights that are not updated during training with back propagation. So they usually come in two types. Ones that we've specifically chosen to keep constants while we train, and also there is some that are a product of batch normalization layers, and they're updated with the mean and variance, but they're not trained with back propagation, and that's why we're seeing that, because we've used back propagation. Okay, what we need to do now, let's train the model. And what we'll do, we'll create some checkpoints so we can save the model weights. We can we'll monitor the validation loss, and we will import them as callbacks as well. And we'll also use the plot loss as callback. But I'll discuss that in a moment. Let's just get coding. So checkpoint, model checkpoint, and what we want to do is call it model weights. And we want to set that as a HH5 file. And then we want to monitor the validation loss and save weights only. We want to put true. We don't have to save the entire model architecture. Mode is minimization. And verbose, we'll set that to 0 because we don't need to have the updates each iteration. Okay, the callbacks. So the callbacks are going to, what we're going to do is use the plot losses callback and checkpoint as well that we just defined. So what the plot losses will do, it'll have a sort of animated graph, and it'll update the accuracy, and the loss and things like that as the model trains in real time. And I mean, this can be done with TensorBoard, but it's just, you have to go into the terminal, and it's a right kerfuffle to do that. We can just do this in our notebook by using the plot losses callback. Not a problem. Okay, so let's define batch size. There's also another parameter you can experiment with. And okay, so let's start fitting the model. So we'll define as history fit. So we need to pass in our data gen train, and we need to have it flow from X train, Y train, batch size to batch size, which we defined. And what we want to do as well is shuffle equals true. We need to set the, that should be okay, so we'll go outside that now. Steps per epoch, and we'll set that to len train by batch size. Okay. I'll tell you what we'll do, just to make this a bit less ugly. Move that there. Move that there. There we go. Validation data. We set that to our data gen val flow, and again we have to pass in the x val, y val, batch size equals batch size, shuffle true, cool. What else do we need to do? We need to, let's set the epochs as well. Epochs, let's set that to 30. Again, experiment with it, and then callbacks equals callbacks, which we've defined here. And we should be good to go on that. And once we hit go or run the cell, it should train. Let's hit it. There we go. Now it shouldn't take that long to train. We'll basically have a graph here soon after the second epoch. But what I'd do, I'll just pause the video, allow it to train. But as you let yours train, just take a look at the graph and see what it's doing as it updates, and and make notes of what your interpretation are of the model import, the model performance. And I'll see you in a moment. Okay, training done, and as you can see, the model's done pretty well. We haven't done too much. We haven't really messed around with any hyperparameter tuning or anything like that. The model architecture is quite simple, and it seems to have done quite well. We've got an accuracy of 75, and a val accuracy of 75 as well. So back in 2017, 75 was state of the art, and we're achieving that now with very minimal effort, very minimal thinking about what we're doing and whatnot. So it'd be interesting if you were able to experiment with various different hyperparameters in things like the augmentation and whatnot. It'd be good to see if you can improve on that and increase the performance. Okay, so what we'll do now, we'll evaluate the model, and let's do the model evaluate. Let me just get rid of that there. Xval and Yval. So if we run that, there you go. We get the 75%. So it's not too bad. Okay, so let's take a look at the metrics, and we'll import Seaborn as SNS. Well, we won't actually, we won't have to use that actually. So Y true is our MP argmax Y val 1. So our true values are stored as one hot encoded vectors, and we need to get the class representation, and we do that by using the argmax on the horizontal axis. So that's why we've done that. And then our Y pred is MP argmax model dot predict x val 1. Okay. and we will print the metrics classification report, and it's y true, y pred, and if we run that, we'll get this back. Why is it not doing that single array? Okay, and that's because I haven't closed my bracket there. There we go. Run that. There we go. So yeah, weighted average 0.75, and it seems to be doing really well on the squiggle class and the narrow banded DRD, but it seems to be struggling with these the narrow band and the noise as well. So that's quite interesting. Now that is something you could probably look into a bit further and see if you can improve on that, because that's obviously what brings the accuracy down overall. And it'd be interesting to see if we can get that above 75%. I'm sure we can, if you were to, tune some hyperparameters, do some more augmentation, maybe set the values different, even add more, or even take some away. Just take a look at that and experiment with it, and post in the comments any improvements on the model, and just explain to other users as well how you've done that. It'll be a great learning experience for everyone involved. But that pretty much brings us to the end of our the Data Scholar Code Along. So as always, thank you for joining me. I appreciate the time, and I hope you enjoyed and of course learn something through this particular session. I'll catch you next time.